Okay, so here we go, beginning chapter 8, and again looking a little bit more at the integral and how it's applied. Let me just talk about something simple. We know that if we have any function f of t dt, and we're looking at the integral from a to b, that it's going to equal big F of b minus big F of a, where big F is an antiderivative of little f. And so what this is essentially showing with any definite integral is that it's a change. It's essentially a net change. A lot of things could be happening between a and b on f, but this is simply the difference between f of b and f of a. And so that's the net change of the function cap f from a to b. Okay, so here's an example. Suppose we're given velocity, which is described as v of t, and the question is, what's the displacement over this interval? So we know that if we integrate velocity from 3 to 5, we get s of 5, the position function, minus s of 3. And right here, this is a net change. And this is an example very similar to ones that we have looked at before. And we have already understood that displacement represents the net change in the position. So let's look at an example that's a little different. Okay, so here's a more, well, it's a different problem than you've seen before. We have oil leaking from a tanker at a given rate. And notice the units. Units are very, very important here. Gallons per hour. And the question is, how much oil has leaked after 10 hours? And so what I want you to understand is that the amount that we're looking for will be equal to the integral from 0 to 10. Now notice the units. 2000 times e to the minus 0.2t dt. Now let's take a second and think about that. The units here are gallons per hour. The units here are hours, and so the units for this entire expression will be gallons. Gallons per hour times hours will leave us with gallons. So at this point I'll have to assume that you know how to do this integration, and what it comes out to be is about equal to 8,647 gallons. So it's the amount of gallons at 10 hours minus the amount of gallons at 0 hours. And what that is, as we've said at the chapter, is net change in gallons. So this is a problem that looks pretty complicated. There's really three pieces to it. The weight of the bucket, the weight of the rope, and the amount of water in the bucket, the weight of the water. And you want to be reminded that work is equal to force times distance. And what makes this problem interesting is force, or weight, pounds, is changing constantly. So here's what we'll look at. On the bucket is x feet high. The water weighs. Okay, take a second and think how much that water is going to weigh when the bucket is x feet high. Did you get the right answer? If we look right here, if x is 0, in other words, that hasn't even begun to be lifted yet, the water will weigh 16 pounds, which is what it was when we started. If x is 20, then that's going to be 4 times 20 is 80, divided by 5 will be 16, and the total weight is 0. So this is a linear equation that describes the fact that it starts at 16, and after 20 feet, it's at 0. And also, when this bucket is x feet high, the rope is going to weigh this much, because there'll be that many feet of rope left. And remember, the bucket is always going to weigh 5 pounds. So therefore, the total work is going to be the integral from 0 to 20 of the force, which is basically the weight. So it's 16 minus 4x over 5 plus the weight of the rope plus the weight of the bucket. So that unit is all pounds times feet, and what we get is about 276 foot-pounds of work. And that is the total amount of work that's done in the case of lifting this bucket of leaky water. So we call this the leaky bucket problem. And it's one of those classical type problems. And that concludes our work in the first section in Chapter 8. So we'll come back a little bit later and we'll find out techniques of getting area between two curves. See you later. Ciao, ciao.